Welcome to the video on equilibrium of a rigid body. So, unlike our last video that we went through, equilibrium of a particle, in this section we're going to be learning about bodies where the forces all don't go through one similar point. So, the biggest example of this are beams. Because you can have forces in the middle, you can have forces down at the end. You also have reaction forces. So as you can see, there's not one similar point in here that all the forces go through. So therefore, it's going to be equilibrium of a rigid body. Whereas in our last example, we had a system that looked like that, where all the forces coincide at one similar point. However, the steps are still going to be the same. So in this video, we're going to go over beams, or particularly simply supported and fixed. We're going to learn how these are different, what it means, and more specifically, what reactions are associated with each of these beams. So, let's start out by looking at a simply supported beam. So when someone says simply supported beam, all that really means is that the beam is going to be fixed, or it's going to be pinned on one end, and there's going to be a roller at the other end. Now, you might be asking yourself, why do I care? What does this mean to me? These reactions here at the end of the beam are extremely important because those are going to tell you where and how to apply external forces to the beam. These are the things that are holding the beam in place and keeping it from moving throughout space once forces are applied to the beams. So if we first look at this pin connection, all this is telling us is that when the beam is pulled on in this direction, it can't move. This beam is not going to move in that direction when it's being pulled that direction. This pin is holding it in place in the X direction. Similarly, the beam isn't going to move in the Y direction when it's being pushed up right here. There's going to be no movement in the Y direction. It's holding it in place there. However, if there is a force applied out here, there is going to be rotation. So, for a pin connection, we know that it is free to rotate. However, there is no lateral movement in X or Y. So now let's look at the roller connection. So this is as if there was a beam sitting on some sort of a wheel down here at the end. So you can visualize with me for a second. If you pull on the beam, you grab hold of it right here and you pull that way, the beam is going to move, right? This wheel right here is going to allow it to move in that direction if you're pulling it in that direction. So therefore, the roller connection is free in the X, or more specifically, in the direction parallel to the surface. The roller is resting on. And I want you to think about it that way, because if you were to have a column where there's a roller up here, this is your surface that the roller is resting on. In this case, it's free to move in the Y direction. So this is your surface. This direction is parallel to your surface, so therefore this is the direction that it's free in. All right, now coming back to here, if we push up on it from down here, this roller is going to hold it down. So there is going to be no movement in this direction. So no lateral movement in Y, or direction perpendicular to the surface. And then also, similarly to the pin connection, if we applied a force out here, this beam is going to be free to rotate. So free to rotate. Oftentimes when you're drawing them by hand, this is typically how you draw a pin and a roller. However, in textbooks, they might get a little bit fancier. That might be kind of what your pin looks like. Your roller sometimes will look more like a rocker in textbooks, something like that. As you can see, this is still free because it kind of rocks on here, so it's still able to move, have movement in that direction, where this one holds it in place in both the X and the Y. If you're not sure in your textbook what something is, there's usually a table that identifies all of this in your textbook. And you can go there, or you can Google it. Google has the answers to everything, right? Okay, so if we look at an example now, we'll just make this one really simple to begin with. So we have our simply supported beam. And let's just put a point load right in the middle. We'll say that's 10 pounds. We'll say this full length is 20 feet, so that's going to be 10 feet. This is going to be 10 feet. And we want to find the reactions at both ends of the beam. All right, so step 1. What is step 1 always going to be when solving a statics problem? Always, 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 always draw a free body diagram. Always, 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 always. I can't emphasize that enough. If you can draw your free body diagram correctly, chances are you're going to solve the problem correctly. Again, this is very visual. Visualization of these things is super important. So, to draw a free body diagram, we always start with our object. So that's our beam. So we can go ahead and draw that there. And then we can apply our forces. So in this case, we have our 10 pounds. And then we want to apply the forces being caused by our reactions or our supports. So you're going to apply reactions in the directions where they're not being allowed to move. So from this information right here, we're going to be able to know how to draw our reactions onto this beam. So anything that's keeping that beam from moving in any direction or any rotation, you're going to draw a reaction. So over on this end, we'll label this end A and this end B. On A, we have a pinned connection. So that means that there's going to be, the pin is going to make it so there's no movement in the Y direction and there's no movement in the X direction. So we'll label this force AY and this one AX. Now we can come to the B side of the beam and we see that there's a roller right there. And so what that tells us is that there's going to be, the roller is going to make it so there's no movement in the Y direction. But for the roller, you can move in the X direction, so we're not going to have an X reaction on that side of the beam. So we'll just go ahead and label this one BY. Okay. And that's your free body diagram. Depending on how detailed you want to be, you can put distances in here. I like to. Just so that way I can just look at my free body diagram. I don't have to be scrolling up and looking in a bunch of different places. So now we can just use this diagram to solve our problem. So once we have our free body diagram, our next step is going to be to write our equations of equilibrium. Now again, this beam is not moving in space. It is stationary, it is static. Therefore, all of our forces and all of our moments need to add up to equal 0. If they didn't equal 0, then our beam would be moving through space. But because it's being held down by our supports and our reactions, we know that it's stationary and it's static. So all of our forces, all of our moments are going to add up to equal 0. So now you can just start with sum of forces X, sum of forces Y, sum of moments. I personally like to always start with sum of moments about point A. That's just what I always do. I like to stay consistent. You can start with any of the equations you want and you're going to get the same answer. Once we go through it though, I'll show you why it's a little bit easier if you start with the moments. But again, you can start wherever you want. I feel like it flows a little bit nicer if you start with the moments though. So I'm going to do my sum of moments about A. You could do your sum of moments about B, and you'll again end up with the same answers. I just like to stay consistent, and I always start on the left side of the beam. That's just what I do. So our sum of moments are going to add up to equal 0. And then at this point, you just arbitrarily pick a direction to be positive. You can pick either direction. It doesn't matter. Again, you're going to end up with the same answers. So I'm going to pick going clockwise as being positive. Again, you can pick counterclockwise. That's totally fine. You're going to end up with the same answers. All this is doing is making it so if our answer comes out to be positive or negative, it means that we picked wrong or we picked right. So I'll explain that a little bit more as we go on. But again, I'm just arbitrarily picking clockwise to be positive. You can pick counterclockwise and you're going to be just fine. You'll get the same answers. So if we take our moment about A, which is this point, here I'll pick a different color so you can see it. And this point here, we know that our moments, to calculate a moment, we take the force times by its perpendicular distance to the point in interest. So, starting over here, we have AX and AY. However, those forces go straight through the point, and so they're going to cause no rotation because their moment arms, their perpendicular distance to point A is 0. So they cause no rotation. You can visualize in your head right here, if we were to push up on that point, it's just going to move point A straight up. Nothing is going to rotate about that point. So there's no moment caused there. Same with AX. So we're done with AX and AY. We can continue down the beam and we hit our 10-pound force. Whoops, let me switch back to black. So we have 10 pounds, and its moment arm is going to be its perpendicular distance from the force to the point in question. So perpendicular distance is going to be that distance right there, which is 10 feet. Okay. Now we can look at that, and as this force pushes down, we know that the beam is going to want to rotate that way. The beam is going to want to rotate clockwise around point A, so therefore this is going to be positive. All right, so now we're done with that force. And we can move on to our next one. So we move down the beam and we run into BY. And we're going to multiply it by its perpendicular distance, its moment arm, which is 20 feet. Now, as BY pushes up on this beam, like that, the beam is going to want to rotate counterclockwise about point A. So we know that this is going to be negative. All right, so now we've reached the end of the beam. So we've reached the end of our equation. So our sum of moments about A are going to equal 0. So now we have this equation. There's only one unknown in it, so we can solve for BY. So BY is going to be equal to 10 pounds times 10 feet divided by 20 feet. Now, something I like to do, if you noticed, as I was writing out my moment equation, that I put my moment arms in brackets rather than parentheses. The reason I did that is because I like to be able to, when I'm done writing my equation, I like to easily look and make sure that every force has a moment arm. Sometimes you can get going through these really fast and you have so many numbers running around in your head that you've kind of forgotten what you've been multiplying, what you've been adding, what you've been subtracting. But this is just a real easy check for me. When I'm done with my equation, I can look and say, okay, BY has a moment arm, 10 pounds has a moment arm. Okay, we're good. Just from experience, it's really, really, really easy to get working through these problems and just leave off one moment arm. Another thing I really like to do is just go back and double check at this point that I've got my positives and negatives correct. Again, it's really easy to get going through and writing these equations and just totally space that you forgot to check which direction these are actually supposed to be going. So 10 pounds is going to push down, which is going to cause that beam to rotate about point A in a clockwise fashion, which is going to be positive, and BY is going to cause it to go counterclockwise, which is negative, which is what we have. So we're good. We can go ahead and calculate BY. Which I get to be as 5 pounds positive. So, and once we reach this point, our BY comes out as positive, so we assumed the direction correctly, so we can rewrite this as BY equals 5 pounds up. Now, again, the reason that it's up is because we drew it as going up right here. When we drew this, we just arbitrarily put directions in. Now, if this would have come out as negative down here, then what we assumed up here would have been wrong, and this would be going down right here. But it came out positive, so we assumed right up here, so we know that this right here is going to be up as well. It's going to be positive. All right, so now we have our BY. Now we can look at our sum of forces Y. Again, those forces are going to equal 0 because our beam is not moving, it's static. And again, we just pick a direction as being positive arbitrarily. I like to choose up as positive. Again, you can choose down, just be consistent so you don't have to worry about it or get confused halfway through your problem. It's just easier if you pick one direction and stick with it forever. So I've picked up. Up is going to be positive for me. All right, so now we just go from the left to right of the beam and we add up our forces. So we've got a positive AY. Next, we've got a negative 10 pounds. And then a positive BY. Those are all our forces, and those are going to equal 0. Again, I like to go through and double check. AY is up, positive. 10 pounds is down, negative. BY is up, positive. Okay, we're good. Now, we solved for BY in the last problem, so we can go ahead and plug that into this equation. AY minus 10 pounds plus BY, which was 5 pounds, that equals 0. So now we've got one unknown, so we can solve for AY. So AY is going to equal 10 pounds minus 5 pounds, which is going to equal 5 pounds. Again, this is positive, so we drew our picture up here correctly. And so AY is going to be up. Now, really quickly at this point, if we would have drawn our free body diagram, like this, and done our sum of forces y equals 0, up is positive, we're going to get a negative AY minus 10 pounds plus BY. So we're going to get negative AY minus 10 pounds plus 5 pounds equals 0. We can solve for AY, and that's going to equal negative 10 pounds plus 5 pounds, which is going to be equal to a negative 5 pounds. So because this came out negative, we know that we drew this arrow in the wrong direction. So AY equals 5 pounds, direction opposite, that's what this negative means, opposite of what we drew here. So it's going to be up. Again, we get the same answer either way. So that just tells us it doesn't matter how we draw our picture up here. It just matters that we identify it in our answers what direction it's going. Again, you see we get the same answer either way, but that's just what this negative here means and the positive here means. All right, so we've got our AY and our BY in this picture up here. So the only thing left to do is sum of forces X. Now you can write out this equation, but from inspection you can see that the only X force that's acting on this beam is AX. So AX has to equal 0. Again, you can write out that whole equation. All that's going to look like is we need to pick a direction. I like to choose to the right as being positive. So then we would go across the beam from left to right. We've got AX. We keep going all the way to point B. There are nothing else. And so then that equals 0. So AX equals 0 pounds. All right, so again, we found AY, we found BY. That's all we've been asked to find in this example. Find the reactions at both ends of the beam. We found AX, AY, and BY. And those are your final answers right there. Nothing really else. One thing you can do is redraw your free body diagram with the values. I won't draw AX because it's 0. So that's what that beam looks like. And why this is important is because later, when you actually design these systems, you're gonna have to know that whatever is holding this beam up has to be able to support that 5 pounds. Otherwise, whatever's holding up the beam is going to fail. So that's why that's important later on. All right, so now that we've looked at simply supported, let's go ahead and look at a fixed beam. Whoops. All right. So when drawn by hand, a fixed beam look something like that. So it's completely fixed at one end over here, and it's free at the other end over here. There's nothing at this end that's holding it up. Another name for this is a cantilever beam. All that means, again, is it's completely fixed on one end and it's free out on the other end. Similar to a diving board situation. So, if we consider as we did the simply supported beam, if we look at this support right here, this is like having a beam stuck in the wall. So if you push up right here, the beam can't move in the Y direction. If you pull in the X direction, the beam is again gonna stay right there. The beam isn't gonna get pulled out of the wall. And for this case, when you apply a force over here, the wall is holding this beam fixed right here, and there's gonna be no rotation. It's completely fixed right here. So if we were to draw a free body diagram of a fixed beam, you would draw your beam. It can't move in the Y direction. It can't move in the X direction. And it also can't move in rotation. So you're going to have a reaction Y, a reaction X, and a moment reaction on a fixed beam. All right, so let's do an example. Let's say we've got a fixed beam that is 10 feet long, and let's say there is a uniform load being applied to this cantilever beam, and we'll say that this is 2 pounds per linear foot, 2 PLF. All right, and we'll label this side over here A, and we want to find the reactions. Again, the reactions are what hold the system in equilibrium. It's what keeps this beam from moving through space. Okay. Now, the first place we want to start, again, is what? Always, always, always draw a free body diagram. Always, always, always. So first you draw your object, which in this case is a beam. We apply our forces, which is our uniform distributed load of 2 PLF. And then we apply our reactions. And we only have reactions at A because the other end of the beam is free. So for this, like we discussed above, we're going to have an AY. We're going to have an AX. And we're going to have a moment reaction at A. Again, you can draw these arrows in any direction. These are completely arbitrary. We're guessing right now. When we solve our equations of equilibrium, we will figure out what direction they're actually going. All right, so now that we have our free body diagram, and put a length on this beam of 10 feet. Now that we have the free body diagram, we can move on to step number 2, which is equations of equilibrium. Again, I like to start with the moment equation. So I'm going to do that again. And the reason I like to do that is because it only gives you one unknown. If we go back up and we look at the equations we wrote for the previous problem, you can see in our sum of forces y we have 2 unknowns, but we had already solved for one using that moment equation, so then we only had 1. If we did the forces y equation first, then we would have 2 unknowns. We'd have to do the moment equation, then we'd have to come back to the forces y equation and plug it in. So you kind of have to take kind of an extra step, or you kind of have to loop back if you want to do sum of forces y first, which is fine. You're going to, again, get the same answer. I just feel like it flows a little bit better if you do the sum of moments first. So, following that same practice, we're going to do sum of moments about a equals 0, and then just pick a direction that you want to be positive. Again, I like to do clockwise. It's just what I've always done, and that's what I'm used to. So we're doing it about point A. So AY is going to push straight through that point, only causing translation, so the moment is 0. Same goes for AX, and then we have MA. And that is drawn in the positive direction. So that's going to be positive. So we've got MA. And now we have this distributed load that we need to deal with. So to find the force associated with this distributed load, we know that it's going to be the area under the curve. So area of a rectangle is base times height. So the base is going to be our length, which is 10 feet, times our height, which is 2 PLF. Now, we've got that force, and it acts through the centroid of a rectangle, which is halfway. So this is going to be 5 feet, and this is going to be 5 feet. So the moment arm for our distributed load is going to be 5 feet. Now, looking at this right here, if we're trying to rotate about that point, this is going to push down on the beam and try to cause it to rotate clockwise around point A. So therefore, this is positive. Okay, so now we continue to work our way down the beam, and those are the only forces. So we're done with this equation, and that equals 0. We can do a quick check. So we've got brackets to go along with our distributed load, and MA is already a moment, so we don't need brackets on that. So we're okay. We have moment arms for everything. Check the directions. MA we have going in the clockwise, okay, positive. Distributed load, force it to go clockwise, so that's also going to be positive. So we're good on our moment arms, and we're good on our signs. So we can go ahead and solve for our unknown, which in this case is going to be MA, which is going to be equal to 10 feet, negative 10 feet times 2 PLF times 5 feet. So we're going to end up with 100 pound-feet, which is negative, right? Because that's a negative 10. So negative 100 pound-feet. So again, this negative sign means that it's going in the opposite direction than what we drew it in our free body diagram up here. So MA is actually equal to 100 pound-feet going in the counterclockwise direction. So now we have our moment reaction, and we just need our X and our Y reaction. Again, we can just look at our free body diagram up here and notice that AX is the only force acting in the X direction. So therefore, by inspection, AX equals 0 pounds. All right. Now we can move on to our sum of forces in the Y direction. Again, I like to choose up as being positive. So we'll start at the left side of the beam and we run into a positive AY. And then our distributed load is going down, so that's going to be negative. Again, our force from that distributed load is going to be the area of a rectangle, which is just base times height. So base, which is our length, is going to be 10 feet. Our height is going to be 2 PLF. And we keep going, and those are the only forces. So that's going to be equal to 0. So we can solve for AY, which is going to be equal to 10 feet times 2 PLF, which is going to be 20 pounds. Which, again, this is positive, so we assumed correctly in this image right here. So AY equals 20 pounds pushing up. All right, one thing I want to point out about this problem really fast is when you're looking at these equations, we'll look at this one right here, to make sure that your units are canceling correctly. We know that AY is going to be a force, so like pounds or newtons or something like that. We know that moments are going to be a force times a length. So pound, feet, Newton meters, for example. So if we look at this equation right here, we've got 10 feet times 2 PLF, which is actually 10 feet times 2 pounds per foot. So we can see that the feet cancel and we're going to be left with 20 pounds, which is a force, which is what we want for our reaction. So therefore, our units are correct. If your units don't cancel correctly, you probably multiplied something wrong or you did something weird along the way. So you're going to have to go back and kind of do some troubleshooting to figure out where you went wrong exactly. If you have any questions about that or you get stuck in any way while you're working on a problem, check out our homework help page. This is where you can submit specific questions you have about homework, specific parts where you're getting stuck and you just need a little bit clarification, something's not working out correctly. We can work on it for you and kind of step by step go through that problem and explain why you're getting tripped up at that specific point in that problem. It is good to point out, though, that our homework help service, we're not going to do full homework problems for you. We're just going to look at a very specific question you have about a homework problem. Again, say you get stuck or you just don't really know how to get started, we can answer that specific problem, that specific question for you, but we're not going to get a full problem from you, do your homework for you, and then send it back to you. That's not what we're here to do. We're not here to do your homework. We're here to help you learn. If you are just having struggle about these problems in general, you can go ahead and check out our tutoring page, where we can either sit down with you in person and go through homework problems with you step by step, or we can meet with you online and again go through homework problems step by step to help you learn, rather than just have us do the homework problem for you and give it to you. You're going to actually learn how to solve the problems by yourself. Again, if you have any questions about this video or anything else that you find on our website, you can send us an email. So that email is taylorstutoringcenter@gmail.com. You can shoot us an email there, or you can use the chat function at the bottom of this web page.